Alright guys, I'm back with the next lesson. We're going to move on to section 10.4. Just so you guys know, these videos are trademarks, so don't go trying to make money off of them. I'm the only one that can make money off these things, so just so you guys are aware. Alright. Okay, so we're going to talk about section 10.4, and it's titled Use Inscribed Angles and Polygons. So, first of all, let's talk about what an inscribed angle is. We need to define it. Before we do that, let's review a central angle, because it might be important to know what a central angle is, know the difference between inscribed angles and central angles. So, if you remember, a central angle is just an angle whose vertex is at the center of the circle. And its sides are radii of the circle. So, an inscribed angle is different from that because the vertex lies, instead of in the center, it's going to lie on the circle. Okay? So this is the definition. I've got guided notes for you in this section as well. The definition of inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. So I think I left you some room to draw a picture of it, and here it is. So go ahead and fill in the blanks. Just get rid of this altogether. So right here is going to be an inscribed angle. Angle ACB is an inscribed angle. Okay, so just to show you the difference between an inscribed angle and a central angle, let me draw a central angle here that intercepts the same arc. And by the way, this arc right here, AB, is going to be the intercepted arc of this inscribed angle. Okay, it's the arc on the interior. So, and I actually think I have that defined here. So let me scroll down and you guys go and write this down as well. And again, pause wherever you need to. So, an intercepted arc is the arc that lies in the interior of an inscribed angle and has endpoints on the angle. So here it is. That arc right there has, let me just make sure I apply it correctly. So it's the arc that lies in the interior of the inscribed angle. There it is. And its endpoints are A and B. All right? The endpoints are on the angle. So that's an inscribed angle, and so let me compare it to a central angle like I was mentioning earlier. So if I draw a central angle that intercepts that same arc, let's say that's the center. I'm just kind of guessing where the center would be. Hopefully I got it right. Let's say it's approximately there. Well, the central angle that intercepts that same arc might look something like that. So obviously you guys can tell the difference here between a central angle, which is the one in green that I just drew, and the inscribed angle, which has a vertex on the circle. Okay, so this vertex is at the center. Should make sense that that's a central angle. This vertex is on the circle. That's an inscribed angle. It's the biggest difference. So scroll down a little bit if you need to fill in the guided notes there. That's the definition of intercepted arc. Now, there's really in this section, we're going to talk about one important fact about inscribed angles. It's the main focus of this section. Now, there's going to be other things we talk about as well. So let's go ahead and get into that. Well, you can kind of maybe guess what's going to be special about an inscribed angle. At least you know maybe a little bit about it. So if you look at the central angle, look at the arc it intercepts. Now, if you remember, if we had a central angle, so let me give you an example here. So let's say this is, I'm just going to make something up here. Let's say this angle is 150. So just to review from section 10.2, if that angle is 150 degrees, then that means its intercepted arc is 150 degrees. So that would be 150. I'm just making some numbers up here. So if that central angle is 150, that arc is 150. Well guys, if you look over here at this inscribed angle, hopefully you can tell that it's going to be less than that central angle. Now how much less, that's what we're going to get into. But it is definitely going to be less than that central angle that intercepts the same arc. Okay, so how much less? Let's go ahead and write that down. Here it is. This is called the inscribed angle theorem. So it's the measure of, let me read it real quick. It says this: the measure of an inscribed angle is half the measure of its intercepted arc. All right, so fill in those guided notes there. Inscribed angle is always half the arc. Sorry, I think I bumped the camera. Hopefully it didn't move too much. Alright, so fill that in, and let me go ahead and scroll down here. So this is what we're saying, guys. So the measure of angle ABC, that angle right there, again, just want you to notice that that's an inscribed angle. the measure of that angle is going to equal half the measure of the arc that it intercepts. So guys, AC is going to be the intercepted arc from there to there. So let me just bring up a quick example. So how about we use that same example we did last time. So let's pretend this is 150 degrees. Okay? So if that's 150 degrees, then the inscribed angle's got to be half of that. All right? The inscribed angle is always half the intercepted arc. So if that's 150, what would angle B have to be? I'll pause. What's angle B going to be? Anybody? Okay, you might have already said it by now. 75 degrees. It's going to be that angle. All right, 150 divided by 2. Half of 150. All right, it's 1/2 of the measure of arc AC. Another way you can think about this is that the intercepted arc is going to be double the inscribed angle. So you could say that as well. So 75 times 2, 150. So if you've got the angle, just multiply it by 2 to get the arc. Pretty simple. All right, there's not a whole lot to remember with that fact. You just got to know the inscribed angle is half the intercepted arc. So let's work through some examples. I've got you some examples there. 2 examples we're going to go over here real quick. So the first one is just reviewing this concept. See if we know how to do this. So let's find, and by the way, I have this listed. If RT is the diameter, I've got that written down on your guided notes. We want to find both of these things. So let's find the measure of angle T, which I have written down, and the measure of arc QR. I've got that written down as well. So here's the picture. Let me scroll down to it so you guys can see it. Draw that picture. We want to find 2 things here. Angle T first, and that one shouldn't be too difficult. And the measure of arc QR, that's going to be a little bit tougher. We got to find a few things before we can find that. So let's see what we got here. Now guys, a problem like this is kind of like a puzzle. You got to find one piece first before you can fill in other pieces. So angle T though we can find right away. Hopefully you notice it. So I'm going to highlight it in green again. So look at this angle right here. All right. So that angle I highlighted in green, what type of angle is that? So think to yourself this. You can answer it out loud if you want. If you said inscribed angle, you are correct. So that is an inscribed angle because its sides are chords of the circle and its vertex is on the circle. So if that's an inscribed angle, the fact that we just wrote down is that the measure of the inscribed angle is going to be half the intercepted arc. So guys, look over here, I'll highlight in red. Hopefully everybody agrees that that is going to be my intercepted arc of that angle. Okay? So if we know the arc's 48, all you got to do is take half of it. And so what do you get? Well, half of 48 is 24. So this answer is 24 degrees. Measure of angle T. All right. The next one, arc QR, it's going to take some, like I said, we're going to have to figure out a few things about it. Well, it might be important, if you just look up here, it might be important that RT is a diameter. Why did it give us that information? Well, there might be a reason, it might not, it might just be useless. It's possible. That happens. They give us information we don't even need. But we might want to use that, so let's just kind of find something here first. What I'm trying to say is, guys, I don't have an inscribed angle whose intercepted arc is QR. Alright, so I might have to do a little different method here to find QR. Alright, so let's think about this. Well, is there an arc that I could find? Well, what other information am I given? Well, hopefully you guys notice we do have this 50-degree angle. And again, what type of angle is that? It's going to be inscribed. So if that's an inscribed angle, 50, and let's say we wanted to find this arc right here, QT. Well, the fact that we just wrote down is that an inscribed angle is always going to be half of its intercepted arc. So 50 is half of what? If you said 100, got it. So that's 100 degrees. But that's not our answer. Hopefully you guys are aware of that. So that's going to help us though. If we can find that to be 100, let's use the fact that we know about RT being a diameter. Okay? So if RT is a diameter, hopefully you guys remember from, I think it was the first section of this chapter. It might have been the second. So 10.2, if we have a diameter, it's going to divide this into 2 semicircles. And if you remember, how many degrees are in a semicircle? Well, if there's 360 in a circle, there's 180 degrees in a semicircle. So all we've got to do here, if we know, and I know I'm doing a lot of highlighting here, guys. If we know this is a semicircle from there to there, and if we've already got 100 degrees of it, all we've got to do is take 180 minus 100, and that'll give us the measure of that arc. So that should be 80 degrees. So let me write this in. So arc QR is 80 degrees. So that right there is 80. It's supposed to be an 8. 80 degrees. Okay, so we're done, guys. That's an answer. That's our answer for QR. Hopefully that made sense. That's not, I mean, if it wanted us to find, let's say it wanted us to find TS, you do something similar. You take 180 minus 48, and that would give you this arc, TS. Okay. So there we go. That's one example of using the inscribed angle theorem. So let's move on. The next one. Now this next example is going to lead us into the next fact. Okay, the next theorem. Now the next theorem doesn't really have a name, but if we can figure out this next example, we'll understand better the next theorem that we're going to write down. So here we go. So in this one, go ahead and read it. It says find the measure of arc RS and the measure of angle STR. What do you notice about angle STR and angle RUS? All right, so let's try to find these two things first, and then we'll answer that question next. All right, the second question, or the second part, I should say. All right, so here we go. Well, there's only one angle given to us, guys. Hopefully you noticed that's 31. So if that's the only angle given to us, again, notice what type of angle it is. What type of angle is that? Well, it's not a central angle. It's going to be yes, inscribed angle. Okay. So if this is 31 degrees, this inscribed angle, the intercepted arc, hopefully you guys notice or are aware, that right there, RS, is going to be its intercepted arc of that angle. Okay, well, that's all well and good, but what can we say about that arc? Try to find it. All right, I'll pause right here. Figure out what that arc's going to be. And you should be able to find it like this as long as you know the fact. I'm snapping my fingers. You should be able to figure it out like that. So all you got to do is multiply that by 2. Okay, the inscribed angle is always half the arc, so that means the arc, the intercepted arc, is double the angle. So 31 times 2, 62 degrees. So let me write this out. The measure of arc RS, we just found 62 degrees. First part done. Okay. Next thing we want to find is the measure of angle STR. Okay, so we're trying to find STR. Well, that's this angle. I mean, highlighting green here. That's that angle, STR. Okay, well, same principles apply, guys. Look at this angle. Isn't that an inscribed angle? And so if I asked you which arc does it intercept, well, doesn't it intercept the same arc? It intercepts RS here, which is 62 degrees. So if that angle intercepts that arc as well, I mean, the facts don't change. Inscribed angles still have to be half their intercepted arc. So this guy's got to be half of that. So therefore, this guy has to be, drum roll, 31. It's got to be 31 degrees. So let me write that down. Measure of angle STR is equal to 31 degrees. Okay, getting somewhere. Now the next thing, and we need to answer that last question. It should be pretty self-evident now. So watch what happens. What do you notice about angle STR and angle RUS? I wonder. Yeah, they're going to be the same. All right, hopefully you notice that. So let me write this down. Angle STR and angle RUS. Let's say congruent. And is that just a fluke, or is that always going to happen? If two angles intercept this, sorry, let me repeat that. If two inscribed angles intercept the same arc, do you think this is just true in this one case, or is it always going to be true? And hopefully you said it's always going to be true, right? So I could draw, if I wanted to, I know it might get kind of crazy in here, but if I wanted to draw another inscribed angle that intercepts the same arc, what does that angle have to be? Well, 31. Okay, it has to be that same angle, so it's got to be 31 degrees. Okay, hopefully that made sense. And I could keep drawing them all day if I wanted to. So let's keep going. The next thing is to define what an inscribed polygon is. Actually, no, sorry, I'm getting ahead of myself. We need to write down this theorem. So we talked about it, we need to write it down now. So this theorem says this. If two inscribed angles of a circle intersect the same arc, then the angles are congruent. So what should go in the first two blanks is inscribed angles, and the last blank is congruent. Okay, so let me draw a picture of this. I left you some room to draw a picture, so this is not much new here. I mean, this is essentially what we just did. Okay, so let me draw it in green here. So let's say we have this inscribed angle, and I'm going to draw the other one in blue. Let's say we have this inscribed angle. All right, so let's say we wanted to call that point A. Let's say we want to call this point B. Why don't we call this one C and this one D? So if this happens, so if angle ACB and angle ADB, they're intercepting the same arc, which is arc AB, then what we can say is the measure of angle ACB is going to be congruent to the measure of angle, the measures are going to be equal, my bad. So the measure of that is going to be equal to the measure of angle ADB. There it is. So again, just really quickly to wrap this up, that angle right there has to be equal to that angle right there. It has to be congruent. Okay, those angles have to be congruent. There we go. So that's a picture of it. All right, moving on. So now we're going to get to inscribed polygons. An inscribed polygon is a polygon in which all vertices lie on the circle. And that shouldn't be much of a stretch, guys. I've got a picture there for you. If an inscribed angle, if its vertex is going to be on the circle, then an inscribed polygon, all the vertices are going to be on the circle. Alrighty. Moving on. So that's what an inscribed polygon is. Now, the last theorem that we're going to look at is going to deal with inscribed polygons. Sorry, not the last theorem, but the next theorem. Take that back. Sorry, guys. Yeah, I guess it kind of does deal with inscribed polygons. So it's about right triangles. Okay, so here we go. Let's go ahead and write this down. So we'll get to a theorem dealing with this, but we're going to kind of shift gears here. I'm going to try to introduce it to you. All right, so let's try to understand it first. And this would go in the next picture on your guided notes. Okay. So the last page is what I'm talking about. The very first theorem on the last page. Draw this picture down in the place where I have the picture drawn. Okay. So here's what I want you to think about. What if we had an inscribed angle whose angle is 90 degrees? Okay. And by the way, this would be an inscribed right triangle. Okay. So what if that was a right angle? Well, guys, we know right angles are 90 degrees. So let's think about this. Well, using the fact that we already know about inscribed angles always have to be how much of their intercepted arc. Try to do that without looking. Try to remember it. All right, so let me say that again. Inscribed angles have to be how much of their intercepted arc? And the answer is they have to be half. So guys, if that guy's 90, what would this intercepted arc have to be? The one I just highlighted in green. Well, 90 is half of what? The answer is 180. So that guy would have to be 180. Well, if we have an arc that's 180 degrees, what else can we call that? Well, it's half a circle, right? So that's otherwise known as a semicircle. So this guy's going to be a semicircle, and so what does that mean about this segment? Well, that segment is going to divide this circle into two semicircles, and what do we call a segment that does that? Think about it. Okay, hopefully you've already answered. It's a diameter. Okay, that's got to be a diameter. So the one in purple that I just traced over there. So let's go ahead and write this down. So the fact that we just figured out is this. If a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle, and the converse is also true. So if we wrote that backwards, so if we exchange the hypothesis and the conclusion, that fact is going to be true as well. So let me read this again. If a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. The converse is also true. Okay? So what we're saying here is, guys, this. The measure of angle ABC, which is an inscribed angle, okay? And by the way, this whole thing is an inscribed triangle because all the vertices are on the circle, okay? So if the measure of angle ABC is equal to 90, I misspoke. Let me read it again. The measure of angle ABC is equal to 90 if and only if, remember IFF means if and only if, segment AC is a diameter. So you can read this one of two ways. You can say if segment AC is a diameter, then that inscribed angle has to be 90. Or you can read it like this. If that inscribed angle is 90, then that has to be a diameter. Okay, those are the two ways to look at this. So you can read it either way. That's what we mean by the converse is also true. All right, so if you flip that and make that statement, that's also true. Okay? So hopefully that makes sense. And let's go ahead and move on to the very last theorem. Like I said, I'm trying to move a little bit quicker in these videos so they're not so long. You can pause them if you need to. Man, I keep repeating myself here. Let's keep going. All right, here's the last one. Here's the last theorem. Okay, I guess I'll leave it up there. I'll try to explain it here in a second. So go ahead and write it down, and then we'll go back and talk about it. So, a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. All right. So to review, supplementary means what? Anybody? Okay. The answer is means add equal 180 degrees. Two angles that add equal 180. Okay. So let me go ahead and write this down. So just to make a note about this picture, and go ahead and draw it as well. So the measure of angle D plus, guys, hopefully you understand what opposite angles are. If we start with angle D, the opposite angle to that is going to be angle F. These two angles, E and G, are going to be adjacent to angle D. Okay, the one opposite is the one straight across. So the measure of angle D plus the measure of angle F has to equal 180 degrees. Okay? Also, the measure of angle E, what's the opposite angle of angle E? Well, it's going to be down there, angle G. That has to equal 180 degrees. That's what supplementary means. Okay, so you can make that note there on that picture. So, guys, I'm going to try to do, I know I didn't give you enough room on your guided notes, but I want to talk about this real quick. I want to explain why this has to be true. Okay? So, let's go ahead and get this thing started. It's kind of like a proof. It's not going to be a two-column proof. I'm just going to explain why it works. So here we go. Let me go back to this. I skipped this circle earlier. And I'm just going to draw a normal inscribed quadrilateral. So just pick 4 points on the circle. And if you have room somewhere, if you can find room somewhere to draw it, you might want to draw it on the back of your guided notes. So I picked 4 points. Just connect them all. Make a quadrilateral. The dots. Okay. So let's say we want to call, how about we call this X? We don't know it, we'll call it X right now. Okay. So let's think about this. X, if you notice, is an inscribed angle. Okay, that's nothing new. We've been talking about that this entire section. X is an inscribed angle. That is my inscribed angle X. Okay? So, let's talk about its intercepted arc. I'm going to draw the intercepted arc in green here. So the arc that X intercepts is this guy right here. All the way around. It's probably going to be a major arc, but all the way around there. That is my intercepted arc. So if I wanted to label this, if you think, guys, again, the main fact you need to remember is that an inscribed angle is always half of its intercepted arc. So what that means is the intercepted arc is going to be double the inscribed angle. Okay, So if that's x, how do we write double x? Hopefully you guys know it's going to be 2x. So we can call that arc 2x. Okay, so now the next thing I want to refer to, I'm going to highlight this arc here. I want to refer to the arc from here all the way around. What's left of the circle? You guys, hopefully you guys see what I mean there. This is what's left of it. The one in green is one arc, and then the rest of the circle is this arc I just drew in red. Okay, well guys, it doesn't really matter what this is. I don't really know what it is yet. It's 2x. I could let this be some number, and if that makes more sense, you can substitute a number in there for it. If you want to let it be like 60 or something, you could. But let's just say, okay, we'll call this x. That guy's 2x. Then how would we denote the rest of this circle? Well, how many degrees are in a circle? Everybody should know that. The answer is 360. So if there's 360 degrees in a circle, what's left over? If I've got 2x right here, the leftover has got to be 360 minus 2x. So for example, I'm just going to give you a numeric example. I use the example 60 here. So if x is 60, then 2x would be 120. This would be 360 minus 120, which would be what, 240? Okay, so I'm just making numbers up here. Obviously, x probably isn't going to be 60 because that's going to be obtuse, but you guys get the idea. I'm just making a number, picking a number at random. So we know that arc. And so now that we know that arc, and by the way, this will be in degrees. Okay. Well, the last thing I want to talk about is how can we find, or how can we write this angle? And I'm running out of colors here. So I'm going to use black. I'm talking about this angle, the angle opposite it. So that angle right there. Well, doesn't that angle intercept that arc? And isn't that angle an inscribed angle? So again, I'm going to state this fact. Hopefully it's getting clear now. An inscribed angle is always half the intercepted arc. Another way of saying that is if we divide this by 2, it's going to give us the inscribed angle. So guys, off to the side, think about this. What's 360 minus 2x? What's half of that, or what's that divided by 2? Now remember, when you take two terms divided by 1, you need to divide both terms by 2. Okay? So what is 360 divided by 2? Answer, 180. What is negative 2x divided by 2? The answer, negative x. So look at this. This angle is going to be 180 minus x degrees. Now, I don't know if you see it yet. Look at these two. What's the relationship between x and 180 minus x? I'll give you a hint. If we add them together, what happens to the x's? Well, x plus negative x, the answer is 0. So what are we left with? 180 degrees. So what does that mean? Well, what did we just do here? We added them together, and we found that they equal 180. So what's another term for that? Hopefully you guys got it. What we call that is we call those supplementary angles. So these two have to be supplementary no matter what x is. All right, so moral of the story is, hopefully that made sense when I went over this, a little proof here, showed you why this theorem's true. But if it didn't, you just need to remember the theorem. The opposite angles of an inscribed quadrilateral are supplementary. Okay, so let's do a couple more examples, and then we'll call it a day. All right, I'll end this video. So here we go. So 2 parts. Find the value of each variable. What we need to do. All right. This one's pretty simple, I think, as long as you remember that fact that we just wrote down. So first of all, diagnose what we have. It's an inscribed quadrilateral. Okay. So if that's an inscribed quadrilateral, well, the fact that we just learned was the opposite angles have to be, that's right, supplementary. So in this case, 80 plus x, because what supplementary means, they have to add to equal 180. Okay? So all we got to do is subtract 80 from both sides. So x has to be 100. We got one of our answers here. We would do something very similar for 75 and y. Those are opposite angles, so therefore they have to be supplementary. So that means they have to add to equal 180. Then I'm going to subtract 75 from both sides. And 180 minus 75, I'm going to scroll down a little bit, y is going to equal 105. All right. So we know those have to be true because of that fact that we just wrote, that theorem. Okay. You guys try this one without me. Pause it, and everybody needs to try this. All right, so hopefully you paused it. Now, here we go. So again, this is another inscribed quadrilateral. It's inscribed. We've got all four vertices on the circle, and so therefore we know the fact is if you add the opposite sides together, it should equal 180. They have to be supplementary. So 2x, the opposite side to 2x is 2x. So therefore 2x plus, my bad, I misspoke. Not the opposite side, the opposite angle. Okay, I don't know how many times I said that. But yeah, the opposite angles are supplementary. Misspoke. Don't make that mistake like I just did. So if we add those two together, that has to equal 180. That's what supplementary means. 2x plus 2x is 4x. All right, divide by 4. X is going to equal, I think 45. Yeah, doing my head here, 45. So that's it. Okay, the last thing, 4y and 4y and 2y, those are opposite angles, so they have to be supplementary. So to finish this, it's going to be 4y plus 2y equal 180. 4y plus 2y is 6y equals 180. And so divide by 6, y is going to equal 30. Okay, that'll wrap it up for this section. It's kind of a longer section. I don't know how long this video was, but hopefully that makes sense. And I'm going to leave you an assignment to practice this stuff. Okay, thanks. See you guys.